All right, here we go into the second podcast of Week 9 Chem 30. And we are officially into Le Chatelet's principle, making some sense of some of the interesting changes that were demonstrated in the two YouTube videos of the previous lesson. Now, our focus this podcast is on changes in concentration. So all I mean by that is if you add a certain chemical that's part of an equilibrium, or you remove a specific chemical that is part of an equilibrium, what sort of a shift will that stress cause on the equilibrium? So check it out. Ultimately, what Chatelet came up with is he said if you have a system that's already at equilibrium, but you disturb it, and by disturbing it, that means you change one of its properties. In other words, you add a stress, and stresses can be changes in concentration, they could be temperature changes, they could even be doing something like compressing the system, okay? Then anytime you mess with one of those properties, the system in turn is going to respond. And how does it respond? There's the important word. It will always try to oppose this change. So this is the whole classic thing that if you put a force on something, it will exert an equal but opposite force back, right? So ultimately, any stress potentially can cause one reaction to be occurring faster or slower than the other. By one reaction, I mean either the reverse or the forwards. And then, in turn, the system will shift and you'll reach a new equilibrium state. Now, we'll analyze each of these stresses separately. And like I mentioned, this first stress that we'll look at momentarily is about concentration. Regardless, though, anytime you look at an equilibrium system that has a stress put on it, we look at it in three different sections. The first one is called initial equilibrium, and this would be before any stress is applied. So just what we see to begin with. Once the stress is applied, we start to go into a shifting non-equilibrium. It's not at equilibrium because it is shifting. It's responding to the stress on the system. It's opposing the stress on the system. The third step is a new equilibrium. It's the result. So in turn, a new equilibrium will mean new concentrations for each of your products and your reactants. Now, these are going to be proportionate still with each other, but it will still be a shift. Now, ultimately, the great thing about Le Chatelet's principle is it lets us make predictions about how systems will respond to different stresses put upon it. So even with the demonstrations from the previous podcast, we now, after we talk about Le Chatelet's flow, we could say, okay, what will the system do, for example, when I add chloride ions to it? Oh, naturally you added chloride ions, the system wants to get rid of the chloride ions because that's the opposite. How does it do that? By reacting them away and favoring the forwards reaction. All right, let's put this into more of a specific context then to concentration. Step by step, I wouldn't honestly say just memorize this. I'd say look at it, make sense of it, because logic doesn't need to be memorized. It makes sense. If we look at scenario 1, where we add a chemical, ultimately adding a chemical will cause the system to do the opposite, which is use up the chemical. It's sort of like you give someone money. What do they want to do? Well, they want to spend the money. They want to oppose what you did. So by adding that chemical in an attempt to use it up, there's one of two scenarios that can occur. If a reactant was added, it'll favor the forwards reaction to try to use up the reactant. Vice versa, if a product is added, it's going to favor the reverse reaction to try to use up the product and go back to the reactants. Look at another scenario. Adding was the first scenario, removing a chemical is the second scenario. Similar type thing. Think of an opposite. If you take something away, the system is naturally going to try to make more. It's going to try to produce more of that same chemical. So scenarios, if you remove the reactant, then it is going to try to make more reactant and favor the reverse. If you remove a product, vice versa, it's going to try to make more product, thus favoring the forwards reaction. like I mentioned, truly logical. Okay, consider this particular equilibrium system. And this is one that does have a color context to it. We're not going to focus too much on the color for this one. We're going to look more about relative concentrations. So we start with hydrogen gas and iodine gas. Yes, I know iodine is a solid at room temperature. Hey, guess what? This equilibrium system doesn't exist at room temperature. So that means that we are dealing with three gases. Okay, the formation here is hydrogen iodide gas. So we end up with a scenario where all three entities are present at the same time, albeit in potentially different concentrations. Now, this is the type of graph that you'll see in relation to Le Chatelet's principle. In this week's assignment, you're going to have to draw these graphs for a few questions, and for others it's already there. So read the question, pay attention to what it says. But ultimately, what you have to do is always start with the three entities or two entities, or really however many reactants or products there are, and show their concentrations initially. Now, you'll notice that all three of these, their initial concentration isn't wavering. It's staying straight, right? Straight across, straight across, straight across. That's very intentional. At equilibrium, concentration doesn't change. It's not going up or down. The only thing that makes the concentration change is a stress imposed upon it. Hint, hint, that's coming. So first scenario, we're going to add some extra hydrogen gas to the system. Now to what system? Well, to this system, guys, the one that I was introducing you to before. So consider what happens if we increase the amount of hydrogen gas. Then system is naturally going to try to get rid of it. How does it get rid of it? By reacting it, which means the system is going to favor the forwards reaction, right? It always does the opposite. You add hydrogen gas, the system tries to take it away. If it favors the forward reaction, then that means that you are going to get more of the hydrogen iodide gas, and in the end, you're going to get less of the hydrogen gas and iodine gas, after, of course, that initial big jump in the hydrogen gas. Okay, let's go back to our graph here. Now, I color-coded these. I find it a lot easier so you don't get mixed up with the lines. I want you also to remember, proportionately, we have 1 mole of hydrogen gas reacting with 1 mole of iodine gas, producing 2 moles of hydrogen iodide gas. Let's start with the hydrogen gas. Initially, we add more. Now, this is important. You're going to see when you add a chemical, there's a sudden, huge, sharp increase straight up in concentration. So that'll be the first thing. We're adding H2 gas, so that bam, big sharp up. Then the system responds by reacting it. If it reacts it, the concentration is going to go down. So show that shift going downwards. Then at equilibrium, it'll be perfectly flat and straight again. Why? Because it has reached a balanced new concentration. Now, iodine is doing the exact same thing. Why? Because it's also a reactant. Hydrogen's a reactant in this equilibrium. Iodine's a reactant in this equilibrium. I don't have a sudden sharp increase though, because I didn't add iodine. It's just naturally being reacted. Now, of course it's reacted. That's not the shape I wanted. How could it not be? The hydrogen gas has nothing to react with unless the iodine gas is reacting too. So both of them are being reacted. This will always follow the same trend. Any chemicals that are on the same side of the equation, either reactants or products, will always show a similar trend to how they behave, according to Le Chatelet. Vice versa then, hydrogen iodide is on the opposite side of these two. It's the product. So if these two are going down in concentration, the hydrogen iodide is going to go up. Now, proportionately, remember that it is a 1-to-2 ratio. There's 2 moles of hydrogen iodide. So we're going to see then that this goes up at a faster rate. Come on, pen, work. Than what the other ones did. And I know it's a little bit hard to definitely see from a picture perspective, so I usually write it, I'm like, okay, this is going up by times 2 because it's 2 moles produced. this is going to go my iodine down by times 1 because it's 1 mole reacted, and the hydrogen gas is going to go down by times 1 because it's 1 mole reacted. There you have it, guys. This is our graph showing, according to what you would predict by Le Chatelet's principle, the effect of adding hydrogen gas. I cannot stress enough, though, that initial sudden going up of hydrogen gas that exists because we added it. Nothing else had a sudden increase or sudden decrease. They were more gradual because they were simply responding to the shift in the equilibrium. Alrighty, let's check out another one. We're going to look at the same system, but in this case, instead, we're going to remove the I2 gas. I'll call your attention back to that original equation again. I'll write it down here for you. We've got hydrogen gas, 1 mole of it, reacting with iodine gas, again, 1 mole, in an equilibrium system produce 2 hydrogen iodide gas. If I remove I2, so it doesn't mean it's all gone, but I remove a part of it, then similarly, it's going to be suddenly removed. So if you suddenly remove it, the concentration is going to take a sudden dip for that iodine. Nothing else is going to suddenly go up or down, but the iodine will. Now, think about what the system does. You removed that iodine, so naturally the system wants to make more because that's the opposite. Do you make more by reacting it away, or do you make more by producing iodine? Well, of course by producing it. How do we do that? We favor the reverse reaction. Okay, if we favor the reverse, we will, after taking it away, slowly see an increase in our iodide concentration. Hydrogen is on the same side of the system as the iodine, so it will also show a similar pattern of increase in concentration. Hydrogen iodide, on the other hand, is what's reacting away in order to favor the reverse reaction to produce more iodine gas and in turn hydrogen gas. So our hydrogen iodide is actually going down. Now my graph, I ran out of room for it, but you can imagine this would be a times 2 shift down. It's not really going down to 0. So I'll write that in so it's obvious. Times 2 shift downwards, times 1 shift upwards for our iodine gas, and times 1 shift upwards for our hydrogen gas. Once again, notice hydrogen and iodine are on the same side of the equation and they do the same thing. They're both increasing. Hydrogen iodide is on the opposite side of the equation, so it does the opposite pattern. However, don't lose sight of that sudden sharp decrease of the iodine. Why? Because we removed it. Okay, there we go, guys. Now, please take note. Don't lose sight of this. The actual value of the equilibrium constant doesn't actually change by the removal or addition of the chemical. Yes, the concentrations of each entity can change, but proportionately they will remain the same. So when we work out the equilibrium law and the equilibrium constant, that value doesn't vary with a change in concentration, which by definition is the addition or removal of those chemicals. Questions to continue on with. You already started, I hope, with the previous podcast on number 1. You can now finish it with C and D. In addition, you can move on in number 3, which you started again, I hope, and do C. Good luck with it. Let me know if you got questions. By all means, come to the optional Google Meet on Thursday at 11 o'clock and we can go over things and I can clarify it and chit chat a bit to hopefully give you some greater clarity. Talk to you soon.